This podcast, we are going to be looking at the geometries or the shape that our molecules make in their 3D orientation. So when we're looking at the shapes of our molecules and what they orient, we are going to focus on the central atom. And the central atom is the atom that's in the middle with atoms bonded to it. And how those atoms are bonded to it around the central atom is what dictates the overall shape the molecule will have. There are two types of geometries that we look at when determining the shape of a molecule. The first one is your electron geometry. Your electron geometry is the shape determined by the total number of electron regions. You may also hear the term electron domain or regions of electron density. It all depends on who's using which term, but they all mean the same thing. What this means is around that central atom, how many bonded atoms and or lone pairs are around it, and we will count those groups. Now, multiple bonds, that means a triple or double bond between the center atom and a surrounding atom, still counts as one region because it's just one bond between two separate atoms. And each lone electron pair counts as one region. Once we have identified the electron geometry, we can then identify what's called the molecular geometry. The molecular geometry are the shapes of our molecules that are determined by the VSEPR theory. That's the valence shell electron pair repulsion theory. So we know electrons are negative, and negative repels negative. So as we have electron pairs around our central atoms, they will actually dictate and change the shape of the molecule, as we will see as we go through these examples. One thing to pay attention to is what we call multiple center atoms. So these are larger molecules, so they are going to have two center atoms on them. Every center atom gets its own electron and molecular geometry. We're going to create a table, and we'll put all our information into this table. And so I suggest stopping the video, create this table, and then just make sure you leave enough lines to go through all of our slides. So we're going to start with the most simple molecule. We're going to look at what's called two electron domains. We will use an example. I'm not going to go through drawing the Lewis structure, so if you want to pause the video and draw the Lewis structure on your own, that's just great practice. If not, that's fine. So our first example is going to be SiO2. So here we have our Lewis structure for SiO2. First thing I'm going to do is I circle our electron pair domains. So I have one oxygen bonded to my silicon, and I have another oxygen bonded to my silicon. So there are two electron regions around my silicon atom. This gives us what our molecule looks like. So here we have little models, and these models just kind of help us orient what these molecules look like in their 3D shape. So you can see the double bonds and what it looks like. We're very literal. So if you look at this and look at the way the atoms are, they are linear. So our electron geometry is linear. Then as we go through to determine our molecular geometry, we want to look at how many bonded atoms are there. And remember, we count multiple bonds as one region. So in this example, we have two different sets of bonds present. And on the central atom, there are 0 lone pairs. So remember, I just said on the center atom. Everything is about the center atom when we're determining our geometries. Now, because there are no lone pairs, our molecular geometry is the same exact thing as our electron geometry, which makes life a little bit easier. So our molecular geometry is also linear. These work for molecules that have center atoms. If you have a molecule that's just two atoms, say like hydrogen fluoride, there is no center atom. That is just two of them. And no matter how you orient these are also just going to be linear. So our first example of a linear molecule works for just two atom molecules or molecules that have just two regions around it. Now we're going to look at 3 electron domains. So our first example we're going to do is CH2O. So here's our Lewis structure for CH2O. Again, the first thing I do is I circle all the regions around the central atom. So I have 1, 2, 3. 3 regions. The name we give 3 regions is trigonal planar. The reason we call it trigonal planar, so here's my model kit. We are very literal in how we like to name our things. So if you connect the surrounding atoms, they make the shape of a triangle. And it is on a plane, which means it can lay flat against a surface. Therefore, trigonal planar. So looking at this example, I have 3 bonded atoms and 0 lone pairs. And as we saw in the previous slide, when you have 0 lone pairs, the VSEPR theory does not come into play. So the name stays the same. Therefore, our name is trigonal planar. All right, our next example, SO2, shows us how the VSEPR theory comes into play. So here we have SO2 in our Lewis structure. Again, I'm going to circle all my domains. So I have 1, 2, 3. I have 3 regions. The biggest difference now is the fact that I have a lone pair. So I have 3 electron regions, therefore the electron geometry stays the same, trigonal planar. However, the number of bonds in lone pairs change. Now I have 2 bonded atoms and I have 1 lone pair. What this looks like with my model kit is this. So I have my 2 bonded atoms and I have this little flag that represents my lone pair. But because we can't actually see our lone pairs, if I take this off, it looks different. So here are the 2 together. They look different, therefore we have to name them differently. And so this is where the VSEPR theory comes into play. Valence shell electron pair repulsion. So since there is an electron pair on the center atom, it actually repels the bonded atoms a little bit more, causing them to move a little bit closer to each other. The region that these lone pairs of electrons take up is a lot more than a region that bonded electrons take up. And that is why the molecular geometry name has to change. So again, we're very literal, and this is bent because it is bent. Then our last set, we're looking at 4 electron domains. So we're going to look at CH4 first. So here we have CH4. I'm going to go through and circle. So I have 1, 2, 3, 4 regions. What we call 4 regions, tetra, just like we did with covalent naming. Tetra means 4. Tetrahedral. So tetrahedral looks like this. It is now what we call taking up a 3D space. All right, so now we have to look into the 3D orient, whereas before everything was like on a plane. But with our 3D shape, we need to now take into account its spatial awareness. So here we have 4 bonds. We have 0 lone pairs. Therefore, as we saw before, when we have 0 lone pairs, the name stays the same. So our molecular geometry is tetrahedral. Now, what's kind of cool is when you actually draw these in a 3D shape, which you do not need to know how to do, but I just wanted to represent it to you, is we do a little bit of a 3D drawing. So I put 2 of my atoms on a plane, all right? And then we have 1 atom coming out of the picture and 1 going behind the picture. So we use this little wedge to represent a hydrogen coming out, and we use these dashed lines to represent a hydrogen going behind. And this now represents, to the best of the artist's ability, a 3D nature of our 4-region molecule. Our next one, NH3. So NH3, looking at this one in our Lewis structure, we have 1, 2, 3, 4. We have 4 electron domains still. So it's still a tetrahedral, but we have changed the number of bonds to lone pairs. So we have 3 bonds and 1 lone pair. Therefore, it has changed, right? So if I take my lone pairs off, it does not look the same anymore. So our molecular geometry name has to change as well. And this one is called trigonal pyramidal. It looks like a triangle, it looks like a pyramid, but it's up on a stage, so it looks like it's been pulled up. Those valence electrons have pulled them up. So the presence of that one lone electron pair has caused the shape to change. It looks differently, which is why the molecular geometry, or the name of it, needs to change as well. And our last one, H2O, has 2 bonded atoms and 2 lone pairs. So here's our water. It still has the 4 regions, so it's still a tetrahedral based off its electron regions. But because of those lone pairs, the actual shape it looks like has completely changed. So here's our tetrahedral, right? Here's our trigonal pyramidal. Here is the last one, and this is bent. So as we increase the number of valence shell electrons, or lone electron pairs around the central atom, it changes the way the molecule looks. So you need to be able to draw Lewis structure. You need to be able to figure out bonded atoms and lone electron pairs around the central atom only in order to figure out the electron geometry and then the molecular geometry. And here are 3 examples for you to try on your own. They are in your packet that you have as well, and we will see them in class.